So, I asked you guys to work on some stuff from last time. Let's start making some questions from that homework 5, if anybody has any. Or if you have anything older than that even, that's okay to ask about too, but just let me know. Enzo. Which one? 6. Sure. Okay. So we start by determining that we should have 5 solutions. Using we know that we're going to have the factors of 8 divided by the factors of 1. So that is just 1, 2, 4, and 8. All over 1, but I'm not going to bother to write the over 1 part, right? Figure out what we want to, which one of those we want to use. Let's fire up our calculator. I'm going to go ahead and type that add mama jamma in there exactly as it's written. So I got that typed in. I'll set my window now. So the smallest thing on my RRT list is -8, and the biggest thing is +8. So I'll go ahead and put those in as my X mins and X maxes. And then take a look at my picture. Okay. So it looks like -2, and then it's almost flat on the x-axis until -1. Did you notice that? So I'm suspicious that there might be some other stuff going on in there. So I'm going to zoom in quite closely to that area to get an idea of what the actual x-intercepts are, because it's hard to tell where the things are actually crossing there. Probably more than one in there. So I'm going to go from like -2.5 to -1.5. I'm sorry, -0.5 is what I meant to say. And I'm going to go ahead and take a real close look, and I'm going to go and squeeze down on the y-axis too, from -1 to +1, and really get a tight window there. I don't guarantee that I might not have to squeeze down the y's even a little bit more to get an idea of what's going on, but that's where I'm going to start. So here is intercept over here, and then comes up. We get another one over there. But I'm going to go ahead and take another squeeze down on that, since it seems like that's not going to be a problem. I'm going to really take a good hard squeeze. So I'm going to go all the way down to -0.1 and +0.1 and see if that helps at all. So there's one. There's the other one. Okay, so there is 2 there. And it does appear they're at -1 and -2. So far, so good? Okay. So let's just go ahead and start. I don't know, let's start with -1. Shouldn't matter which one we start with, at least with what we know right now. Oops, that's a 20 there. Okay, so there's that. We'll do a -2. Okay, so that worked. But I'm left with something that I can't. That's right over here. Not a good. I can't factor using my factoring shortcuts, right? Using my tree. Is that okay so far, Enzo? So what should we do? Could be factored more? I don't know. Maybe, maybe not. I'm not sure. What could we try? So let's think about some of the holes in our method right now. So using synthetic division, we can't detect imaginary things. So it's possible this just has a bunch of imaginary parts to it that we can't do anything with that basically make that part unfactorable. The other piece that we can't detect are the multiplicities. So maybe -1 or -2 could be used again. Maybe one of them is a duplicate solution. That could be. It's unlikely there's any irrational things, because when we looked at it, the only we'd still be able to see those x-intercepts for irrational things. They just wouldn't match up to the RRTs that we have. So it's probably one of those two situations, if indeed that is factorable anymore. Really, the only one we could try is doing another synthetic division with either -1 or -2. And if one of them doesn't work, we'll try the other one. And if they both don't work, I would say we're settled there, and that's probably as good as we can do. Is that okay? I don't know, let's... And that did work. And the quadratic that we're left with is definitely something we can factor. That's something that we would have factored first semester. Oh, that's embarrassing. Yes. So multiplies to give us 4 and adds to give us 4, just 2 and 2. The other way you could write, just FYI, is with exponents. So notice how we have 3x plus 2s and 2x plus 1, so I can use exponents to write it that way. Either is okay with me. I prefer to write the exponents because, well, it's a lot less writing. But you don't have to, you know. Now, wouldn't it be nice when we started this problem to know that maybe we could have used, that we're going to have to use some or both of these factors more than once? Would be nice to have known that before we started synthetically dividing, right? We're going to get to that today. So that'll be one of the things that we're going to add to our method today as a way to detect whether that's going to happen, which is super, right? That makes life much, much easier when we know that weird stuff can, you know, when we can expect weird stuff starting to happen. Other questions from this homework. I think this was the sneakiest one. What is your name? Landon. Of course. Working on them, everybody. I'm trying. But this, I think, is the first time you've raised your hand for something, so I apologize. You've been in long enough that I should know it, but I don't know. I just don't. I'll work on it. Okay. So 4 solutions, right, from the exponent. And then the RRT is going to be the factors of 24 over the factors of 1. The factors of 24 is actually 1, 2, 3, 4, 6, 8, 12, and 24. And then we'll have to go look at F after that. So let's do that. So I have x to the 4th minus 4x to the 3rd minus 7x squared plus 22x plus 24. And then we'll reset our window here. Smallest was -24, the biggest was +24. And I'm going to reset my y's to be -3 and +3 again because I don't want to be zoomed in that much. Get a little bit more context to my picture. So we'll do that and hit my graph. See what's going on. So it looks like over here, maybe it was -2 or -3, and over here, maybe, I don't know, 4 or 5. So maybe I'll go -4 to 6 as my zoom, just so I can read the coordinates a little easier. So -2 and -3, and then +3 and +4. Feel good so far, Landon? Okay. Notice I have 4 x-intercepts and I'm expecting 4 solutions, so there can't be anything tricky going on here, right? Just a matter of grinding through the synthetic division now. So any one of these would be good because each one of them is on my list. So I'll just start with -1. That'll get me to here. I could try to factor the polynomial, but it's got 4 terms, and you'll find out pretty quickly it's not going to work factor by grouping. So I should just do another synthetic division. I've done -1. Let's go to -2 then. Doesn't really matter which one you choose next. Any would do. Oops. 14. And that works. So at this point, what you could also synthetic division, I could do another synthetic division here. You could do that also. What's a +3? Excuse me, that's not negative. I wrote that down wrong. So when I do that, I get x -3, and then my leftover is x -4, which is the same thing. Had factored that. Either would be okay to do, but this would be our final answer. Does that feel okay, Landon?
Yeah.
Okay. So depending on which one you feel more comfortable with, doing the synthetic division or doing the factoring tree stuff, you often will have a choice where, well, I could do either one. Do whichever one looks easier, On rare occasion, will you actually need to do one versus the other? Okay. Anybody else here? Five? Sure. Let's see, that's 2, 13, 11, 26. $26. Now go back and double check that one more time to make sure I copied that right. Good. Okay. Right away, I'm using 4 solutions or 4 x-intercepts at most. The RRT is going to be the factors of 30 divided by the factors of 2. So my factors of 30 are 1, 2, 3, 5, 10, 15, and 30. So that's over 1. I also have to do those same factors then over 2, since my leading coefficient has more than one factor to it. But if I look closely at that list, in particular the second line of that list, you'll notice that I have several duplicates on there. So like 2 over 2 is really just 1 that's already on my list. 6 over 2 is really just 3. That's already on my list. 10 over 2 is really just 5, already on my list. And 30 over 2 is really 15. That's already on my list. So I'm just going to cross those out there real quick because I don't need them on my list twice. That doesn't do me any good. If you didn't cross them out, it's no penalty though, right? Like no harm, no foul kind of thing. And then we need to go look at the graph. So 2x to the 4th plus 13x to the 3rd plus 11x squared minus 16x minus 30. Reset my window to -30 to +30. Those are the biggest and smallest values for my RRT. And then hit graph. I'm expecting to zoom in here. Okay, so it looks like all the action is maybe from like -5 or 6 out to negative or +1. So I'll go and reset this maybe to like -7 to +2 just to make sure that I get it all. So there's something. There's something. Did I miss one? Let me double check that I typed that in correctly. So far, so good. Oh, I see what I did. That's supposed to be a 26, not a 16. You ever make a mistake? Happened to me. Couldn't read my own messy penmanship. Oops. Oh, missed my negative sign. There we go. So that's a 26. So graphing it again. Sorry about that, Lily. There we go. Okay, so it still looks like about the same range as I had before would have been okay. But we got some extra stuff going on here. So we'll go again, like -7 to +2, it looks like would be okay. You good with that? Okay. So let's see, what do we got here? This one looks like -1, 2, 3, 4. That one looks like -5. This appears to be a decimal. It looks like halfway in between -1 and -2. So that's -1.5. And this one over here is between 1 and 2. That's probably +1. But we're missing something, right? So there should, at most we could have 4. We're seeing 3 right now. Maybe that matters, maybe that doesn't. What I know right away, though, is looking at these guys, I estimated those, right? Like that could have been 1.4, it could have been 1.6, it could be like 1.45. I'm not really super sure on that. Now, 1.5 is on my list, so maybe that is a legit factor that I could use synthetic division on. But maybe it's not. Maybe it's not actually 1.5. Maybe it's some other decimal that just is pretty close to 1.5 that I can't tell the difference from just looking at the picture. So I definitely would want to start with this one at the -5 first. And then we'll see kind of what happens to see if I have to try to use one of those or not, or if we need to go poking around the graph a little bit harder. But the -5 I feel good about. Lily, does that make sense to you on that reasoning?
Yeah.
Okay. So that does work. If I take a close look at that, I'm relieved to see that I have something that I should be able to do grouping with. So I don't have to make any choices here and just ignore that possible problem that I had with the synthetic divisions and just do my grouping and be gone out of here with without having to do any guessing. So if I make my two groups, from the first group I can take out an x squared, and from the second group I can take out a -2. And in both cases is 2x plus 3. When I factor that out, I'm left with the x squared minus 2. And the x plus 5 kind of continues down. The 2x plus 3 also can't factor anymore because that's linear. And the x squared minus 2 is two terms, but it's not a difference of two squares because the 2 isn't a perfect square. And it's clearly not a sum or difference of cubes because the exponent is indivisible by 3. So that's as good as I could do. If I look at this, this factor would be giving me the -1.5. This factor gives the plus or minus √2, which is about 1.41. So if I tried to do the -1.5, that would have worked. The positive 1.5 would not have. That was really positive 1.41. I just couldn't tell the difference by looking at it. And if we go back and we look at our graph, if I zoomed into this spot right here at -1.5-ish, I would have actually seen there was two x-intercepts there that were very close together. That was the missing one we couldn't see, is that -1.5 and -1.4 appeared to just be one x-intercept when we looked at it initially. Is that okay with you? Now, would it be nice to know if I had like where that extra solution would have come from or would have been at, that other x-intercept? That I would have known, being like, hey, there's another one floating around somewhere. I'm positive that there is. Where could it would have been, right? We'll be able to figure that out today, too, with some of the pieces that we're going to add in. Okay? All right. So let's get after the new ideas today. We're going to see 3 new theorems that'll help us deal with multiple solutions and then like the imaginary and irrational things going on, possibilities going on. So the first theorem is called the bend-bound-straight theorem, and it has 3 parts to it. So the condition is that we have x equals a as an x-intercept for the graph of y equals f of x. Maybe we should say. So if A0 is a bend, then that factor x minus a is used an odd number of times greater than or equal to 3. So what the heck do you mean by a bend? So this is what we mean by a bend. So there's my x-intercept, x minus a. And you see how the graph is coming in curving one way, hits the x-axis and starts curving the other. And by a bend is the graph kind of bends as it's going through the x-axis. So it's curving one, and then it starts curving the other way. You guys kind of see that? Okay. That's what we mean by a bend. So that, again, we could give a really technical definition for what we mean by bends and bounces and stuff. But we're going to be using this theorem visually. We're going to just be looking at pictures and identifying it. So I'm not going to give a technical definition. I'm just going to give you a picture because that's how we're going to use it. So who cares about the technical definitions, right? That x-intercept just gets used an even number of times. So a bounce, it just like hits the x-axis and then goes back in the same direction it came. It's bouncing on the ground or something. Is everybody okay with that idea? Again, it's just a visual definition, so it's hopefully fairly intuitive when you look at it. Like a bend looks like it's bending, a bounce looks like it's bouncing. What do you think straight's going to look like? Going straight through, yep. So again, a straight just looks like it's going straight through. But the straights are used exactly once, which is nice, right? The other ones we don't have a specific number of times. It's like, oh, it's even, so like 2, 4, 6, 8. It's odd, 3, 5, 7, 9, but you don't know exactly how many right away. The straight, though, you know exactly one time it's going to get used. So this theorem would have been really nice on that problem that Enzo asked about, right? Where we had things that got used more than one time. We'd have been able to see straight away at the beginning that, oh, I could keep going on my synthetic divisions. And we'll do some examples here after we route the rest of these theorems and do some graph analysis to try to figure out like the possible situations we could be in and how many times something could get used. Okay. The next theorem is called the irrational conjugates theorem. So the irrational conjugates theorem says for a polynomial with rational coefficients, x equals a plus b root c is an irrational solution to f of x equals 0 if and only if x equals a minus b root c is also an irrational solution to f of x is equal to 0. So what this is basically saying is that these irrational solutions are always going to come in pairs. You're never going to get one irrational solution by itself. This would have been particularly helpful in that question that Lily asked about, where we saw that there's just 3 solutions, 2 of which looked like they were decimal, would certainly indicate to us that there's probably a 4th decimal one floating around there somewhere. And then when we looked at the graph, there was really only one likely place where that could have happened at. I guess the other possibility, Lily, that we had an imaginary there, right? The missing one could have been imaginary also, but we're going to take that off the table right here with this next one. This one is called the complex conjugates theorem. And it sounds quite similar. So let f of x be a polynomial with real coefficients. We say that x is an imaginary solution to if and only if x equals a minus bi is also an imaginary solution to f of x equals 0. So this is telling us that imaginary solutions also come in pairs, which takes away the possibility, Lily, that that stray solution could have been imaginary, because there'd have to be 2 of them. Yes, sir?
It says polynomial with, and then what does that say?
Real coefficients. And now you'll notice that I've been kind of specific in a lot of these theorems about what the coefficients for our polynomials had to look like. In this class, we're only going to deal with polynomials with integer coefficients. So all of these theorems are going to work because integers are real numbers. They're also rational numbers, so we don't have to worry about any of that. All these theorems are going to apply to the problems that we're going to deal with in this course. But there's no reason that a polynomial couldn't have like complex number coefficients, but that's well beyond the scope of this class. But basically what it boils down to is every theorem that we've given can be used for any polynomial that we'll encounter in this class. You don't have to worry about like, ooh, does this polynomial fit the conditions to use the theorem? All the polynomials we'll look at are going to fit the conditions. You know what I mean, guys? So I just want to shoot straight with you there. That yes, those conditions matter, but I'm going to tell you that everything you're going to see meets those conditions. So at least in this class. Okay. So those are the 3 new pieces. So let's do some examples now. Okay. So let's just take an example removing the actual polynomial, and I'm just going to give you the information about the polynomial, and we'll kind of analyze what we think is on here. So we're going to take away some of like the actual factoring piece to it. We're just going to think about like what could happen. Is that okay with you guys? Okay. So you could have 8 solutions or up to 8 factors or 8 x-intercepts, right? Everybody's cool there? Okay. Since I know the constant term, the leading coefficient, I can write down my rational roots list. I'm going to have my factors of 6 divided by my 5. So my factors of 6 are 1, 2. My factors of 5 are 1 and 5. So I have that list then divided by 5 also. Everybody okay there? For my graph, my x-intercepts can clearly see are these. Now let's look at these x-intercepts and try to decide whether they are rational or irrational. How do we do that? We check to see if they're on our RRT list. Is -6 on our list? Yes. So that tells me that this is rational. That's something I could use the synthetic division with. Is -1.5 on that list? No, right? It would have to be one of these fractions, and all the fractions are less than 1. Everybody agree with that? Since it's a decimal, we know it would have to be a fraction from that list, and all those fractions are too small. So that didn't do that. Likewise, the 4.5 would have to be irrational for the same reason, right? Okay. Let's look at the bend, bounce, and straights to decide how many times that particular solution could be used. So if I look at -6, is that a bend, bounce, or straight? That's a bounce, right? Because x-axis and then going back in the same direction. So that's a bounce. How about the -1.5? So I know the bends and straights sometimes get confused. Like when we're talking about it, really only look at the part like by the x-axis. Look at just the part in the green box. What is that? That's straight. You know, the same idea here. Like we're just at like that part of -6. So just look at the piece right around the x-axis. I think makes it a little easier to see what's going on. Sometimes the rest of it gets distracting. And the -4.5, straight. Bounce, 2 times, 4 times, 6 times, 8 times, etc. But could it really be used 8 times? We have 8 total, right? But we have 1 straight here and here. So what's the most that -6 could be really used? 6, right? Because we have only 8 total solutions. 2 of them are coming from irrationals. The other 6 could be coming from the -6. So make a table of possibilities. Okay. And each row in this table is going to write. So the first possibility that we talked about was negatives being used 6 times. 6, 2 is 8. That leaves no imaginaries possible, right? With 2 more irrationals gets us to 6, or 2 imaginary solutions in that situation. Or if 2 times 2 irrationals, that's 4 total. We need 4 more imaginaries to get to 8. Those are the 3 possibilities. So I know that it would be negative 6 is going to be used at least twice. So I'd start by doing 2 synthetic divisions with negative 6. And then look at what I have. And if I can factor it, I'll factor it. If not, I'm going to try to do some more synthetic divisions with negative 6, because I know I should do it. If I can do it more 2 times, it would have to be 4. And then see what I get. And then maybe do it again. Does that kind of make sense to you guys? So I can't tell exactly how many times things are being used, but I can tell when they're going to be used more than once. I can tell how many possible times they could be used, right? So like, although I can't tell right away exactly what to do, I can get a pretty good idea of what I can't do. Does that make sense? And we can see how this could be helpful. Right? In particular, we had some problems last night in the homework, like doing this, having this information would have been a little helpful to us. Let's go and do 1 or 2 now, all the way kind of full. How's that sound to you guys? Okay. All right. Okay, so we'll start, and we know, so we'd have most 6 x-intercepts or 6 factors. And we can use our term, that's 81, divide the factors of the leading coefficient 1. So my factors of 81 are 1, 9, 27, and 81. And since the leading coefficient is 1, that's it, right? There's nothing more to do. Now let's go to our graph and take a look and see what's going on. I have x to the sixth plus 6x to the 5th plus 9x to the 4th. Minus 9x squared minus, and I'll set my window to go from negative 81 to positive 81. Those are the biggest and smallest things on my list. I certainly will expect it on this, but we'll start all out there just to make sure there's nothing cool happening. Okay. So both of the things have like right next to the x-axis there, y-axis right there. If you weren't paying close attention, you wouldn't see it happen, but it did. So I think that I can safely eliminate all the way down to negative 3. So let's just go from negative 3 to positive 3. And then try it again. Okay. I have x-intercepts here at negative 3, somewhere between negative 1 and negative 2. I don't know, like, what do you think? Like negative 1.7? Decent sounding S to you guys? Closer to negative 2 than it is to negative 1. One looks like positive 1.7, right? You guys good with that? Now let's do the bend, bounce, and straight. Actually tell negative 3 whether that bend, bounce, or straight with what I have graphed here. I don't think so. I need to see what side, right? So I need to take my window back a little bit further in the negative direction. So maybe I'll go to -4. Just so I can make sure I can see that. Aha! I'm glad I did, right? Because that turns out to be a pretty important piece of information that I would have been missed if I wasn't careful there. -3, is it a bend, bounce, or straight? Bounce. Good. And the -0.7 is a straight 3. And the since it's a bounce, I know it was 2 times, 4 times, but I can't get to 6 times because my limit is 6, and I already have 2 spoken for me as the irrationals, right? Everybody agree? So I make my table here of what could be going on. Oops. So I could be U206 or U2, but I can't have any more -3, can't have any less -3, because it has to be at least 2 and it has to be less than 6. Basically, those are 2 possibilities, right? Is that cool? So we'll start our synthetic division. We have to use the -e to test. And we're going to have to use -3 at least twice, maybe 4 times. We're not sure yet, but at least twice. When we go set up this polynomial, what do we have to make sure notice about this polynomial? If you go back and you look at polynomial, there's something important that you need to make sure you notice there. Excellent. Yes, we're missing our x to the 3rd. We're going to need to have that 0 there. Again, it's easy to forget to do that. Dealing with these bigger polynomials, you frequently see I'll give you things missing pieces. Why? Because your teacher's a sneak, and like the problem's just more interesting often when there's more interesting problem. So I want to point out right here, if you had stopped at this point, the 4-term polynomial you're left with is, I'm not 2, because I know that I can still do their division with -2. I can at least 1, hoping that so twice, then constant x squared, 3rd, x to the 4th. So x to the 4th minus 9. Let's try to factor that then. Something that's got 2 terms, we should be able to figure that. First thing I check is if it's a difference of 2 squares. Is it? Oh, it's even. It's got a minus. And the next thing's a perfect square. So I can certainly factor that to x squared. Can I factor either of those? No, right? The x squared minus 3. The 3 is in a perfect square. Obviously, it's not of 2 cubes or sum of 2 cubes. X squared plus 3 is an addition problem. And then clearly not a difference of cubes. So that's it. One piece that we're getting with this 3. This piece is the 2 imaginary pieces where we're getting plus or minus I3 from those. If you were curious. But we were just asked to factor. So this is that was our factored answer. But I figured I'd put to you like solutions-wise what's going on. Yes, sir.
What would happen if you only got you got 2 rational, 1 irrational?
So that can't happen. The irrational conjugates theorem dictates that they have to come in pairs. The irrationals always have to come in 2 pairs. So that, I mean, it happened, but your polynomial wouldn't have rational coefficients. You'd have like a square root as a coefficient. It would never give you a problem like that in this class. That's what was going on. But like, we're not going to talk about that situation. Well beyond this class. Does that feel okay?
Yeah.
And those are good questions. Those are good if questions, right? Like the weird thing that could happen, I'll be honest with you, like, is that something you'll encounter or not? And like what would need to happen for you to encounter that? So yeah, that's not something we'll have to work on. I think at any level as a high school student, you would see would not see that. A lot of the rules that we have, everything kind of falls apart in weeks. Okay. Probably have time to do one more. Do you want to do one more? Okay. 15 minutes or something. I can probably squeeze another in here. So let's do another one. Got this bad mama here. But the fact that it's a big polynomial doesn't really change much for us. We're still going to do everything exactly the same. The length of the polynomial is kind of material to us. Change how many synthetic divisions we have to do or whatever, but going to change the way we start the problem. So I'm going to go ahead and grind through those first 3 steps from last time real quick. So the degree is 7. There's 7 solutions. The RRT is just be the factors of 4 divided by the factors of 1. And the graph, well, we'll just plug the thing into our calculator and take a peep at what we get. And I'll set my window. So the smallest is -4, the biggest is negative or +4. But I'm going to do -5 and +5 from the lesson that I learned in the previous one, where in case I do get a 0 at one of the ends, I want to make sure I can see past it to tell if it's a bend, bounce, or straight. So I'm going to tack a little bit of extra on there just in case. Okay. So let's see. We got something at -1 and at positive. Both of them are on our list, so they're both rational. -1, is that a bend, bounce, or straight? That looks like a bend to me, although, agreed. And the +2, a bounce, I agree. So since it's a bend, that means like 3, 5, 7, etc. Bounce, 2, 4, 6, etc. But I know we can't 7 because I only have a total and the other one has to be used at least twice. And I know I can't get to 6 because I have 7 total and the other one has to be used at least 3 times. Really, we have, 3 and 5 or 2 or 4. So we'll write up our possibilities. We know there are no irrational ones because we can't see them. So could have that, or they're used a minimum number of times. So 3 and 2 more is 5, so I need 2 imaginaries to get to 7. I could have 5, 2, and 0, 0. But that's it. Those are the possibilities that I have to get to 7. Everybody agree with that? So the place I'm going to start with is under this assumption. So I'm going to assume that we're going to use them the minimum number of times and then see what we get. Although I want to point out to you while I'm setting this up, again, be very careful because we have some zeros that go in for this one, or a 0, I guess. Uh-oh. What did I do wrong here? So 7, 6, 5, no 4. 3, 2, 1, 0, okay. That's that. That's that. Oops-a-daisy. Oh no, that's right. Where's my mistake? Oh, this is it. Jeepers creepers. 1 times 1 isn't -2. You ever make a mistake? Happen to me. So again, I know this can be used at least 3 times, so I'm just going to keep rocking and rolling with it. And I know I'm doing good because I'm getting 0 for my last value, right? That's what I'm hoping to have happen. And it worked. Now I'm going to switch to the positive 2's because I know that should work right. I want to point out to you at this step, what I have left at the bottom there is something that I could factor by grouping. I'm going to bypass doing that, though, because I think it'll be easier to just do another synthetic division because I know it's going to work. And now let's see what I have. So I have x plus 1, x minus 2 that got used twice, left over. And that's as good as I can do, right? That x squared plus 1 we can't do anything with. Not a difference of 2 squares because the addition. Definitely not a sum or difference of cubes. So we're done. Good timing. So for your assignment, and again, this isn't due till next Sunday. So this assignment isn't going to go into this most recent homework, or Sunday's homework check. It'll be a week from Sundays. And I'll get that in PowerSchool to reflect that if you forget. Is this homework 6? So I have 3 factoring problems. And then in part 2, I ask you to use your solution to part 1 to solve it. So it shouldn't be so bad. There's only really 3 problems. Because even the second part 2 where you're solving, like, you already did the factoring in part 1. The solving for part 2 shouldn't be really much of anything at that point, right? But that's it.